Hi, I'd like to talk to you about the future of industrial gas turbine engines, specifically for power production. There has been a revolution in the power industry over the last decade. Given the concern over CO2 emissions, there's been a shift away from traditional thermal power towards renewables. Using Germany as an example, looking at the budget of power produced by different technologies, in 2008, only 8.5% of the total power produced was produced by wind and solar power. Only a decade later, in 2018, this rose to nearly 30%. This is a massive increase in a very short period of time, and it is expected to continue to grow. Initially, these technologies were very expensive compared to established ways of producing power, and their expansion was driven by government subsidies. To compare the cost of different technologies to produce power, the U.S. Energy Information Administration compared the levelized cost of electricity for each technology versus the date in which the power plants using this technology would become operational. Levelized cost of electricity is the cost to manufacture the power plant and operate it over its lifetime, divided by the total amount of power that power plant is expected to produce. This cost does not include government subsidies. As a reference, combined cycle gas turbine power plants, represented by a solid blue line, and coal-fired power plants, represented by a solid black line, are included. As you can see, the cost of both wind and solar power plants has come down considerably due to improvements in technology and scale of manufacturing. The more of something you manufacture, the lower the cost to manufacture that component. With regards to wind turbines, size is also important. Larger wind turbines produce more power relative to their costs. Onshore wind has been cost competitive against coal since 2016 and is now cost competitive against combined cycle gas turbine power plants. Solar PV, or photovoltaic solar power, is expected to be cost competitive with coal by 2021 and cost competitive with combined cycle gas turbine power plants by 2024. Offshore wind is more expensive, but it is becoming more cost competitive, and it is expected to approach the costs of coal by 2025. The main reason offshore wind is more expensive than onshore wind relates to its location. Being offshore, wind turbines need a larger structure, either to anchor them to the seabed or support them through a floating platform. This structure needs to be able to cope with rough seas during the worst storms they are expected to be able to survive. Additionally, undersea power cables are necessary to connect these turbines to onshore power grids. And due to their remote location, it is costly to get crews to and from them in order to maintain them. Solar CSP, or concentrated solar power, is also expected to be expensive, though again costs are coming down. Concentrated solar power is a technology where mirrors are used to focus the sun's energy on a spot to produce heat. This heat then drives a heat engine, such as, for example, a steam engine or a Stirling engine, to produce electricity. In summary, though, the key takeaway from this chart is that both onshore wind and photovoltaic solar are already cost competitive with traditional thermal power plants. So even if the concerns for CO2 emissions went away completely, these technologies are here to stay and are likely to become even more competitive in the future. Thus, it's expected that wind and solar will continue to expand and that more and more of the total power produced will come from these technologies. The problem with these technologies, though, is that they are non-dispatchable. And what does that mean? This means that you cannot control the power produced. When the sun shines and the wind blows, they produce power. When a cloud comes over, solar power plants produce less power. When there is more or less wind, wind turbines produce more or less power. And when the sun is set and the wind is calm, they produce no power. If we look at a typical day in Germany, sometime in the future, when the power grid is dominated by wind and solar power, the power demand over that day varies. At night, there is less power demand as most people are sleeping. During the day, power demand rises as people go to work, factories open, people cook meals, entertain themselves, etc. If there is an event like a music concert or a sporting event, there will be a spike in power demand associated with this. If we add to this plot a fictional but representative supply of power from a solar photovoltaic power plant, you can see that at night, when the sun is set, there is no power produced. Power production rises as the sun rises and peaks sometime just after noon when the sun is at its highest. In this example, a storm passes over in the afternoon and there's a drop in solar power produced. Then as the sun sets, solar power production drops back down again to zero. Now, let's add on top of this a fictional but representative supply of power from a wind turbine power plant. The top of the blue line represents the total power produced by both wind and solar. In this example, wind is too low in the morning to produce any power, but as the day progresses, the wind picks up and the power produced in the afternoon and then drops down again in the evening. Generally, more wind is produced during the day. Wind is also driven by solar power. The sun heats up the ground. This heating varies depending on the color and conductivity of the terrain. Darker, less conductive terrain absorbs more heat or more light and heats up faster, while lighter, more conductive terrain reflects more light and heats up slower. The air near the ground also heats up as a consequence, becoming less dense and rises. Elsewhere, colder air from the upper atmosphere sinks back down towards the ground to replace this rising air. And this produces regions of low and high pressure, which drives the wind at the ground. Because the ground can retain this heat, even after the sun is set, wind is still driven at night. However, the intensity of this wind is usually reduced. In this example, between 12 o'clock and 7:30, excess power is produced, i.e. more power than is demanded. Outside of this time, insufficient power is produced. If this grid relied solely on these two power sources, there would be a blackout in the morning and evening and power spikes between 12 and 7:30. Thus, this is not acceptable. However, if we could take the excess power produced between 12 and 7:30 and charge an energy storage device, we could then use that storage device to provide additional power in the evening when there is insufficient power available. In the morning, we would need to take power from some sort of longer-term storage. For instance, if over the previous weeks, more power was produced than needed on each day, we could charge longer-term storage, which could supply power during this period. Alternatively, other dispatchable power plants could be used to fill in. Okay, we've looked at a typical daily cycle. There is also an annual variation in power supply and demand. Again, taking a country like Germany as an example, the power demand is typically lower during the summer months and higher during the winter months. Germany is fairly far north of the equator and so has fairly cold winters but not extremely hot summers. As a result, there's very little air conditioning in Germany, but buildings are heated during the winter months. As a consequence of Germany being north of the equator, both solar and wind, which is also driven by solar energy, produce more power during the summer months and less during the winter months. Thus, there is a seasonal mismatch between supply and demand. Again, if we could use this energy storage concept, we could solve this problem, storing excess power during the summer months and using that stored power during the winter. However, this requires long-term storage. The World Energy Council produced this nice chart comparing different energy storage technologies. On the x-axis, we can see the potential energy storage capacity of each technology, and on the y-axis, we can see the discharge time at rated power. Thus, technologies such as supercapacitors and flywheels on the lower left of the chart can only store small amounts of power for very short periods of time, whereas technologies on the upper right of the chart can store large amounts of power for longer periods of time. I've also added to this chart an estimate of the range and round-trip efficiency for each technology. Round trip efficiency is an indicator of the amount of power that can be supplied from the amount of power which was stored. For example, if one had a round trip efficiency of 90% and one stored 100 megawatt hours of power, one would get back only 90 megawatt hours. I think when most people think of energy storage, they think of batteries. And indeed, batteries can have very high round-trip efficiency. Lithium-ion batteries, for instance, have nearly 100% round-trip efficiency. However, the problem with lithium-ion batteries is that lithium is a very rare mineral, and so these devices are extremely expensive and not practical for long-term storage at grid level. They are used today, though, for day-night cycles. However, they only make up a very small fraction of grid-level storage. Flow batteries offer a potentially less expensive solution for longer-term storage. However, they have much lower round-trip efficiencies. Having said this, there is a lot of research in battery technology today, mostly driven by the popularity of electric cars, and it may be in the future batteries are more competitive against alternative solutions for long-term storage. I'll discuss in more detail 4 technologies which are seen today to be most promising for long-term energy storage. And I'll briefly mention one additional one. Thermal storage is where electricity is used to directly heat a thermal storage device to store excess power. If this heat can be used directly to offset electricity demand, such as, for example, to provide hot water for heating buildings, then this form of energy storage can be very efficient, with round-trip efficiencies as high as 90%. However, if the heat needs to be turned back into electricity through a heat cycle, such as, for example, producing steam and driving a steam turbine, then the round-trip efficiency drops to around 35 to 50%. Over time, thermal storage will lose its heat, and according to the World Energy Council, this sort of technology is suitable for longer storage times than batteries, but not as long as other technologies. Liquefied air energy storage, or LAES, is where electricity is used to liquefy air. Energy is recovered again when the air is reheated and expanded. I know less about this technology, and the anticipated round-trip efficiencies are relatively low, so I'll not discuss this one in detail. However, there is a lot of research going into this, and it may be that it's more relevant in the future. Compressed air energy storage, or CAES, is where electricity is used to compress air. Energy is recovered again when the compressed air is expanded in a turbine. When air is compressed, it also heats up. If the air is stored in a vessel which loses this heat over time, the round-trip efficiency will be lower. This is especially a problem for longer-term storage. However, if this technology is combined with thermal storage, and the heat from the compressed air is stored separately, and then return to the air before it's expanded, the round-trip efficiency of this technology can potentially reach as high as 70%. The problem with this technology, though, is the storage of the compressed air. Because the air is compressed to a very high pressure, any vessel it is stored in needs to be very strong, and as a consequence, such a vessel will be very expensive. If the plant is located near a cave, which can be sealed to the air, then this cost can be reduced dramatically. However, this limits the number of locations where such a plant is viable. Another alternative is to locate such plants offshore. The pressure vessel can be submerged deep in the ocean, and the water pressure can be used to offset the air pressure, reducing the strength requirements of the pressure vessel. This also reduces the cost. However, there are additional costs associated with locating the plant offshore. Still, these additional costs are less than the cost of building such a pressure vessel on land. Pumped hydro is a very mature technology which has been around to store grid-level power for a very long time already. In fact, the majority of grid-level energy storage today is in the form of pumped hydro. Pumped hydro works by reversing the hydro generator and pumping water back up into the lake. Round-trip efficiencies of this technology are relatively high, between 70 and 85%, and this technology can store a lot of power for long periods of time. Of all the long-term energy storage technologies today, this one is the best. The problem with pumped hydro is that because it's been around for such a long time, Most of the available resources have already been exploited. Building new hydropower plants would mean flooding large amounts of land, which might be better used for other applications such as agriculture. So although this is by far the best solution today, it's questionable how much capacity there is to expand it. Finally, we come to power to gas, or PTG. This is where the future of gas turbines are seen to play a role. Power to gas in its simplest and cleanest form is where excess power is used to produce hydrogen from water using electrolysis. Hydrogen can be stored for very long periods of time. Energy is then recovered again by burning the hydrogen in a combined cycle gas turbine power plant. There is no carbon in hydrogen, so there would be only water and some oxides of nitrogen, no CO2 in terms of emissions. If we ignore losses due to the storage of hydrogen, using the most efficient technologies today for electrolysis and combined cycle power plants, then the round-trip efficiency of this would be roughly 40 to 50%. Comparing this to other technologies, it is on the low side. This is even lower when we include the storage losses. Hydrogen has a very low energy density, thus for an amount of energy, the volume of hydrogen is very large, and this would require an enormous storage vessel. Now, one proposal is to use the current natural gas network, and this might be possible at a relatively low pressure, but if hydrogen needs to be stored in its own vessels, then it's likely it will need to be compressed to a high pressure or liquefied. If I assume that the round-trip efficiency of compressing and expanding hydrogen can be done with a similar round-trip efficiency as the highest efficiency for compressed air energy storage, then the round-trip efficiency of this technology drops to between 30 and 35%. And looking in the literature, these numbers are not too far off other people's estimates. There are also proposals to use this hydrogen to produce synthetic natural gas, which would have a higher energy density and would be easier to store. However, this would add carbon to the fuel, which would produce CO2 emissions when the fuel is converted back into electricity. There are also losses associated with this process, as more power would be needed to produce synthetic natural gas from hydrogen. Another idea in this direction is to use hydrogen to produce ammonia, which is one molecule of nitrogen and 3 molecules of hydrogen. Again, this would increase the energy density, making storage easier. It has the advantage that there is no carbon in the fuel, so no CO2 emissions. However, there would be nitrogen in the fuel, making it harder to minimize emissions of oxides of nitrogen or NOx. Fuel-bound nitrogen oxidizes much more easily than nitrogen gas in the air. This is a problem that's encountered before when burning liquid fuels, biomass or coal, which contain some fuel-bound nitrogen species. So there are techniques from that experience to minimize this, but these other fuels have relatively low concentrations of fuel-bound nitrogen compared to pure ammonia. So this will not be easy. Producing ammonia also increases the losses of the system as energy is needed for this process. So just the hydrogen cycle alone already has a very low round-trip efficiency. So one would need to weigh the losses of producing more energy-dense fuels against storage losses for hydrogen to find the most competitive solution. Currently, the main players in the industrial gas turbine industry are hedging most of their bets on hydrogen being the dominant fuel in the future. They see a staged approach where hydrogen initially would be injected into the current natural gas grid. This would raise the hydrogen content of natural gas. One problem with this is that gas turbines are not the only devices which use that gas. So other devices would need to be adjusted to be able to cope with higher hydrogen content. General Electric claim that their 7HA and 9HA gas turbines can already burn up to 50% hydrogen by volume in natural gas. Siemens stated in 2019 that they intend that all of their engines will be able to handle fuel with up to 20% hydrogen by volume by 2020. Many of their engines already can handle more than that, and 100% hydrogen by 2030. Ansaldo also claimed that their GD36 engine can burn up to 50% hydrogen by volume today, and that they have demonstrated in high-pressure tests that their current burner could burn up to 70% hydrogen without any performance degradation of the engine, and up to 100% hydrogen with a reduction in engine performance. So, in summary, there has been a revolutionary change over a very short period of time in the dominant technologies being used to produce electric power. Non-dispatchable renewables already produce a sizable amount of the total power produced in many countries, and this is set to grow as these technologies are becoming very competitive with traditional means to produce power. Because of their uncontrollable nature, it is essential to increase both short-term and long-term energy storage to help keep the power grid stable. Long-term energy storage is particularly important when there is a seasonal mismatch between production and demand. Power to gas, involving combined cycle gas turbine power plants, is seen to be a viable alternative for long-term storage. Round-trip efficiencies are on the low side. However, hydrogen can be stored for very long periods of time. Additionally, existing power plants can be retrofitted with new burners to be able to burn fuels with higher and higher concentrations of hydrogen as new burner technology is developed. And so it is not necessary to build new power plants to take advantage of this, keeping capital costs low. All of the major industrial gas turbine manufacturers are moving in this direction. So that concludes this video. I hope you liked it. If you did like it, please click the like button below. If you'd like to see more videos like this, please subscribe to the channel. Also, if you have any questions or ideas about other topics related to gas turbines you'd like to hear more about, please write them in the comments. And thanks for watching.